Hi, my name is Kumar Aman. I am a student at Nalanda College of Engineering. I recently completed a 4-week online internship in embedded systems at Emertxe Information Technologies. In this video, I will walk you through what I learned during the internship, the small practice exercise I did in the first few days, and the final project I built. My final project is EV dashboard and ADAS warning system. The internship was fully online for 4 weeks, focused on code embedded systems programming. The goal was to build a strong foundation in microcontroller programming, things like GPIO, ADC, timers, potentiometers, and ultrasonic sensors, and communication protocol such as UART through a real hand-on automotive project. Over the 4 weeks, I learned six main basic areas. First is STM32 and GPIO. STM32 is a microcontroller and GPIO is the configuration. The second is ADC and sensors. ADC stand for analog to digital converter and convert the analog value to digital. To, we, the third one is timers and interrupts. Timers are the most important configurations of electronics or microcontrollers. The fourth one is EV control logics. Here I learned how to control EV logics like speed and battery. The fifth is how to build fault detection and alarm system. Fault detection and alarm system is one of the features of my project. And finally, UART communication. This sends the data from microcontrollers to our computer. Bef- During the internship period, I have done four basic projects. The first U is GPIO Blink. We configure GPIO pins to blink an LED light. Here I turn on and off LED using code. The second was ADC reading. It reads values from potentiometers which simulate real sensors like accelerator, brakes pedal, state of charge, and motor temperature. The third was working with timers, and the fourth was building a driver for HCSR0 for ultrasonic sensor to measure distance. Once I was comfortable with the basics, I combined everything into one bigger system. I built an EV control module for speed, battery percentage, torque, and drive modes. Then an ADAS engine for collision warning and blind spot detection. And a fault manager to catch problems like overheating or low battery. And finally, UART telemetry to send all this data out to a computer 10 times every second. I tested each part using test cases before combining everything together. This is the final project, an EV ADAS dashboards. Here's how the data flows. We simulate potentiometers and ultrasonic sensor in a PICSimLab simulator. These, these sensors send readings to the STM32 Blue Pill. The STM32 processes this data, check for fault, and send it out over UART. And finally, a Python dashboard. The computer receives this data and display it live. This setup actually mirrors how a real car works. The STM32 plays the role of vehicle's ECU and UART work like the CAN bus that connect a car electronics. The system has six main basic features: live speed, battery, and range. Collision warning, which alerts when an obstacle is close. Blind spot detection for vehicle on the left or right. Fall detection, for example, the motor overheats, the system cuts power safely. A live UART data link between the microcontroller and computer. And a Python dashboard that shows all of this visually with a speed meter, battery bar, and bird's eye obstacle. To make sure everything's work correctly, I run test cases, checking sensors accuracy, alarm triggers, fault handling, and data reliability. This part taught me why testing really matters in embedded systems. A small bug can cause a real safety issue in a live system. First, I will start the STM32 firmware running inside the PICSimLab. We use VSPE, which is virtual serial port emulator to emulate ports. Here you can see two paired ports, COM1 and COM4. Our simulated PICSimLab is using COM1 port. Com so sorry for mistakes. Our simulator PICSimLab is using COM4 ports, and our EV dashboard will use COM1 ports. Here you can see the configurations in the PICSimLab. COM4 115200. These are the spare parts we used for our project. This is the potentiometer. The first one is the acceleration pedal. The second one is the brake pedal. The third one is the state of charge or SOC. And the fourth one is the motor temperature. These three are the ultrasonic sensors used for obstacle detections. This is the virtual simulator where our data is printed. This is the alert or LED where the status is shown by blinking the LEDs. Let me show you the virtual terminal where our simulation data is shown. Here you can see the data. These are the ultrasonic readings. This is the time to collision. This is the number of collision, and this is alarms and fault detections. We will show this data in the EV dashboard. For first, let me walk you through the STM32 IDE where this project is built. This is the IOC file of the project. Here you can see all the configured pins. These are essentials to show the readings. Now, this is the main.c file of our project. It's under all the logics behind our targets. This is the source file which handles fault detection. This is the communication bridge or UART telemetry configuration file. Now let me open the EV dashboard. Here you can say we are using COM1 port for our evidence. This is the dashboard where the data are shown in the in live time. Let me adjust the pedals. The changes will be reflected in the dashboard. Let the dashboard loads radar. Here you can see the values are shown now. The speed, the battery status, the alarm, bird's eye view, AV modes. Let's adjust the pedals. This is the final project demonstration. Thank you. This is Kumar Raman, an embedded system intern at Emertxe Information Technology.